Hello everyone, I'm Sophia. I'm happy to present to you work that originated from a Dagstuhl seminar last year and that involves many members of our community. This presentation will be about a conceptual model that unifies concepts for variability in space and time. First, some background. Software product line engineering supports variability in space via features and configuration mechanisms. Software configuration management supports variability in time via revision management. The combination of variability in space and time is desired, but there are many challenges. First, we have a growth of research and tools that deal with similar problems. Consequently, there is some redundant research and development and therefore waste of resources. Then, every tool has its own unique ideas, but it's unclear what they are because tools use their own specific terminology like restriction or ambition. And there can be identical terms in SPLE and SCM that have a different meaning. For example, the term configuration. Configuration is used in SPLE to refer to a selection of features, but in SCM to refer to a specific revision. Those are only a few examples. Therefore, the goal was to understand, to categorize, and finally to unify concepts for variability in space and time to exploit their synergies. And second, provide a clear and unambiguous terminology of the concepts. The benefits are multifold. Comprehension of concepts and terminology supports researchers and developers in scoping and communicating their research. It helps relating concepts of both research areas. And, consequently, this provides a foundation for comparing and combining research while preventing redundant development. The construction process of the conceptual model involved multiple steps. In a Dagstuhl seminar last year, both communities of SPLE and SCM came together with the goal of understanding the ontology, methods, and workflows of SPLE and SCM. In a breakout group, we developed the initial conceptual model that documents concepts and relations for variability in space and time, but not their unification. In follow-up research, the initial model served as input to semi-structured interviews. These interviews were conducted together with one tool expert for every tool. The goal was to understand to what extent the initial model captures concepts of contemporary tools that deal with variability in space, time, or both, and which adaptations to the initial model are needed. So for every concept in the initial model, we discussed whether and what semantically equivalent tool constructs exist that map to the model's concepts. Based on the construction mapping, we organized 2 workshops with members of the Dagstuhl seminar, tool experts, and further interested parties from both communities to further refine the initial model. And the result is the unified conceptual model presented here. One among several findings was that our initial model was missing explicit concepts like mapping, configuration, and feature. We also introduced new hybrid concepts that only exist in tools focusing on both variability in space and time. For constructing the unified conceptual model, we selected a set of tools based on multiple requirements. First, tools needed to deal with variability in space, time, or both. For each case, we selected at least 2 tools. Then, the tools needed to deal with problem and solution space. This requirement led to the exclusion of pure variability modeling languages and tools that cover only problem space concepts like features and constraints. Finally, tools needed to be available to us, for instance open source, or where we could connect to a tool expert otherwise. All in all, we selected 10 tools. For variability in time, we selected Subversion and Git. We did not conduct interviews for them as they are prevalent and there is documentation widely available. For variability in space, we selected Feature IDE, Pure Variance, and Zippo. For tools that have both dimensions, we analyzed Echo, Delta Eco, Supermod, Darwin SPL, and Wave. Interestingly, we can see here that such tools emerged since 2013, and still there are new tools that are in development like Wave. Next, I will present the resulting conceptual model. We started the construction by splitting the model in 2 parts. The right side shows the problem space in SPLE, which represents the abstraction of the domain. We consider this equivalent to the version space in SCM. The left side shows the solution space in SPLE, which is the actual implementation, and this we consider equivalent to the product space in SCM. In the model, we introduce unified concepts that represent either variability in space, time, or both. The unified system contains most other concepts and essentially describes the developed system. An option is a high-level abstraction of any variation in space, time, or both. A fragment is the main concept to describe the implementation of a system. Depending on the granularity, a fragment may be an entire file or a line of text like source code, models, or documentation. Next, a mapping connects an expression, for example, a propositional formula, over options with fragments. So it establishes the connection between the solution space and the problem space. The concept configuration exists in different meanings in both communities. To unify its meaning, we consider configuration a selection of options in space and/or time used to derive a specific product. So based on a configuration, a product is generated by tool-specific mechanisms like delta modules that specify which and how fragments are composed. Concepts for variability in space are colored green, while lighter colors represent abstract concepts. A feature option represents the abstract possibility to customize a system in terms of concrete features. Another established concept for variability in space is the constraint. A constraint can be any arbitrary expression, like a propositional formula. That expression is defined over feature options to constrain which combinations of feature options are valid. Concepts for variability in time are colored orange. Those concepts are revision and system revision. A revision is an abstract concept and describes evolution over time. It relates to its predecessor and successor revision. The structure of multiple directly succeeding and preceding revisions represent branches and merges. A revision can be a concrete system revision that represents the state of the whole system in one point in time as used in Git or Subversion. Concepts for variability in space and time involve both dimensions jointly, and they are colored purple. Feature revision represents variability in space and time as a concrete combination of feature option and revision. The feature revision represents the state of one particular feature at one point in time. And there are also two hybrid relations. The system revision determines which feature options and which constraints are enabled in that system revision. We found interesting insights during the construction process of the conceptual model. There was a lot of discussion about terminology. For instance, we discussed variation point versus option as a term to represent variation on a high level of abstraction. Variation point, however, is associated with SPLE as a concept in solution space and not used in SEM at all. Since it was important for us to use generic terms not associated with either SPLE or SEM terminology, we decided to use option. Then we found that all tools incorporate constructs for the 5 concepts: fragment, product, unified system, mapping, and configuration. So those concepts are the intersection of all tools. Next, concepts that we introduced particularly for variability in space or in time aligned well with the corresponding tools, which was an encouraging insight. However, there is no tool that considers system revisions and feature revisions simultaneously. Maybe this is due to an increase in complexity. Finally, in every tool, a mapping connects fragments and options. In tools that cover only variability in time, like Git or Subversion, the mapping is trivial as it only maps a system revision to a number of fragments. In contrast, tools that consider variability in space require more complex mappings, since they additionally need to deal with features. For the validation process of the conceptual model, we asked 2 research questions. First, is the conceptual model of appropriate granularity? That is, are its concepts too fine-grained or too coarse-grained? Like, does one concept represent several tool constructs, or vice versa? And second, is the conceptual model of appropriate coverage? That is, are there any unused or missing concepts? The process to answer these questions starts with a unified model as input to questionnaires as part of a qualitative analysis. In the questionnaires, we asked the experts to map constructs and relations of the tools to the concepts and relations of the conceptual model. Based on the questionnaires, we created a validation mapping that comprised the mapping results for all tools. Then we performed a quantitative analysis using metrics. Our goal was to quantify the fit of the model to the selected tools. The results of the validation are the following. Whether the conceptual model is of appropriate granularity, we found that system revision and configuration seem fine-grained regarding Git and Subversion. This is because in both tools, system revision is synonymous to configuration. Still, merging both concepts is not desirable for tools that deal with variability in space, because there a configuration consists of a set of features. Then, the concept fragment seemed too coarse-grained with respect to several tools that have a more specific understanding of what a fragment is. For example, in delta-based tools like Delta Ecore, there are core module fragments and delta module fragments. However, we decided not to make fragments so specific to avoid the model becoming too tool-specific. In summary, the results show that the conceptual model is of appropriate granularity and that no concepts should be merged or split up. Whether the conceptual model is of appropriate coverage, we found that there are no unused concepts or relations, and there is also no missing concept. Only relations related to distributed development are not represented in the conceptual model. So altogether, the results show that the conceptual model achieves appropriate coverage. To summarize, we integrated concepts for variability in space and time. Members of both communities came together and worked out a conceptual model with concepts of variability in space, time, both, and unified concepts. For validation, we performed qualitative and quantitative analyses. For future work, we plan to formally specify the semantics of concepts and relations, and also to analyze operations of the tools to unify their behavior. Ultimately, the goal is a holistic unification of concepts, relations, and behavior. That's it. Thanks a lot for your attention.